Hi there. In this video, we're going to look at the last section of Chapter 3 called Antiderivatives, and it'll be the last section on Exam 3. So let's get right into it and learn about some antiderivatives. Oops. So there's lots of applications of antiderivatives, and sometimes it's easier to think, because they're pretty abstract, it might be easier to think of them as concrete problem-solving tools. So a physicist who knows the velocity of a particle might wish to know its position at a given time. An engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount leaked over a certain time period. And a biologist who knows the rate at which bacteria population is increasing might want to deduce what the size of the population will be at some future time. In each case, the problem is to find a function capital F whose derivative is a known function f. If such a function exists, it's called an antiderivative. So the idea here is that in the real world with a lot of physical problems, and this is just a few examples, you might only have information from a particular source, which might only give you a limited information about the thing you're actually interested in. And we know what derivatives are, but it turns out anytime that a derivative is present, that derivative, if the derivative itself is what you're getting the information about, that you can work backwards and find an antiderivative to learn something you may not have known before. So from a technical perspective, any antiderivative is just a function, capital F, where if you take the derivative, you get another function, lowercase f, that I'm just going to call f. And so capital F is called the antiderivative of f. And it turns out that every function with an antiderivative has an infinite number of antiderivatives. So if a function has one, it has an infinite number. That might seem complicated, but look at the bottom of the page here, at the bottom of the slide, and you'll see why that works. So both functions below are antiderivatives of f of x equals 2x. So both of these satisfy the definition. If I take the derivative of this, I get that. If I take the derivative of this, I get that. And you can see that because there's two, you can see why it is that there's an infinite number. Because those two functions are almost exactly the same. So before we move to the next slide to further formalize the definition, let's make sure we understand why this is true. So if you take a function like this function is x squared plus 1, it's a parabola, right? So it's just hand parabola, right? Well, look at the other function, x squared plus 2. That's just a slightly higher parabola. So these functions have the same shape. They're just, one is shifted up and down of the other. So it should make sense that shifting a function doesn't change the slopes of its tangent lines. The derivative is the slopes of the tangent lines everywhere. So it should make sense that the tangent line slopes do not change. And so that leads us to the most general antiderivative, which is just you write capital F of x, and then you just write plus c. So the general antiderivative of 2x is x squared plus c. And that should make sense, right? So just any parabola shifted all the way up or all the way down as far as you want to go has the same slopes of its tangent lines. All right, so let's jump in and do some examples. So what if we have f of x equals x cubed? What's the general antiderivative? Well, the power rule tells us when we take a derivative that the power goes down 1. So if we do an antiderivative, the power needs to go up 1. So it's going to be something x to the 4th. But it can't just be x to the 4th plus c, because the derivative of x to the 4th plus c is 4x to the 3rd. So we have to put a 1/4 in front of the x, because in our derivative, in our f of x, we didn't have anything out front here, so it's a 1. So when we take the derivative of this and the 4 comes out, you just get 4 times 1/4 x to the third, which just simplifies to x to the third. And then your c just, of course, is 0. For part 2 of the problem, for part B, we have to find the curve of this shape that passes through the point 2, 15. So what we're going to do is just shift up or down c units until we find the curve, 1/4 x to the fourth, that passes through 2, 15. So we plug in 2, plug in 15, and solve for c. Right? So this is 4 plus c is 15, so c is 11. So our function is 1/4 x to the fourth plus 11. And that's the way a lot of these problems work. You'll be given a function, and then you'll have to find an antiderivative. And if you find the general solution here, it has a plus c. This is called a particular solution. For every antiderivative, the particular solution will be unique if you're given a point. If you do 2 antiderivatives, you need 2 points, and so on and so forth. Either 2 points or 2 derivatives. You just need 2 additional pieces of information. All right, let's look at these two. So for f of x, what function is cosine x the derivative of? And you might say it's sine x. Well, that's close, right? Sine x plus c, right? When you do an antiderivative, if it says general, you have to tack on the plus c. Now, the question might say, find any antiderivative. Then you don't need the plus c. But normally, we look for the most general form. All right, what about part B? X to the n, and n is not allowed to be -1. We will see what happens in chapter 6 when n is -1. So we're doing the power rule backwards. So we have to add 1 to the power. And earlier we saw when we had x cubed, we went x to the fourth and then did 1/4 times x to the fourth. So if n is 3, so it's just n plus 1, and then 1 over n plus 1 times that. And this might look like a complicated formula, but this is just how it works. When you take the derivative of this, the power goes down 1. But before you do that, you have to multiply by this number, right? So the power comes to the front, and then the power goes down 1. So you're going to have n plus 1 times 1 over n plus 1. That'll cancel to 1, and then that just goes away because it's multiplied. And then the n plus 1 just goes down and becomes an n, and the c goes away. So the derivative of this is just x to the n. So that big complicated thing, that's how it goes. Well, that leads us to, well, those are both answers. That leads us to this table. So this is far from a full list, but this is just the type of thing that you're going to see. And these are the general antiderivatives, right? That you have to be thinking backwards. What derivative gave me this function? So we still have our constant multiple rule here, because the derivative of this, right, here we have a lowercase c times f. So whenever you have a multiplication, you just ignore it if it's a constant multiplied. So this c stays. The derivative of f of x, the derivative of capital F is lowercase f of x, and the derivative of c is 0. So when we go this way, you have to be able to see that it's just the inverse process. And so on down the page. So we're going to take these as rules, right? All the rules we had for derivatives, constant multiple, all that stuff, sum and difference. This is just a partial table. It's not intended to be comprehensive. There's many more. So let's do another example. Find the general antiderivative of that horrible looking thing. And you might think, oh, it's quotient rule, because you want to take a derivative, so you think quotient rule. But we don't have a quotient rule for antiderivatives. We only have a power rule. So you need to simplify it first, like we've done in the past with some other functions. Right? So here, I just pushed this radical t up into all these denominators. So 9 divided by radical t is the same as 9 times t to the negative 1/2. Now I can use the power rule here. T over radical t is t to the 1/2. T squared over radical t is t to the 3/2. So what's going to happen when we do an antiderivative? Well, we're going to ignore the constant, because we have a constant multiple rule for derivatives and antiderivatives. And then this, you increase the power by 1 and divide by the new power. Right? So this one's going to be 9 times t to the 1/2, and then divide by 1/2. What's going to happen here? We're going to get t to the 1/2 plus 1. So it's going to be t to the 3/2, divide by 3/2. This will be t to the 5/2, divide by 5/2. And on a test, you can leave it like this. But for the homework, you might want to simplify it, because you may be asked to solve this for one reason or another, or to find the value of c so that the curve passes through a certain point. You're going to want that simplified to do algebra or arithmetic on these things. All right, now we're going to talk about differential equations. In applications of calculus, it is very common to have a situation, as in example 3, where it is required to find a function given knowledge about its derivatives. So what we started with in this section was talking about f, and then learning about capital F of x. In example 3, I gave you f prime, and we had to find f. An equation that involves the derivatives of a function is called a differential equation. These will be studied in detail in later classes, but for now we can solve some elementary differential equations. So what I want you to take away from this is that the main use of antiderivatives in the real world is solving differential equations. Mostly physics, chemistry, and electrical engineering, but they pop up all over the place. Psychology's using them now, sociology, all kinds of business concerns, computer science are using differential equations, because it's you input what you've measured. You can measure the derivatives directly, and then you work backwards to find the function that gave you those derivatives. So it's a very interesting technique, and it's been used for hundreds of years. So here's a good example. So here we have information about a second derivative. And we know that the function passes through these 2 points. So how do we solve it? Well, there's our function. First thing you do is you do one antiderivative. So this is just a 4. So what function gave me a derivative of 4? Well, it's 4x. When we get to here, it gets a little more complicated, because you really don't want to say what function gave me 6x. Instead, just leave the 6 alone and say what function would give me x when I take a derivative. Right? Well, it'd be x squared over 2. Right? So here I'm just using that power rule from a previous slide, right? Increase the power by 1, so it goes from 1 to 2. Divide by the new power. Same thing here, just leave the 36 alone. I know you guys are going to be tempted to just do this stuff all in your head. It's not worth it, guys. Take the 4.5 seconds it takes to write it down and get as many points as you can. You've got to trust me. So just leave the 36 alone. What function gave me x squared when you take a derivative? So the antiderivative is x cubed over 3. Then you tack on a plus c. Then you can simplify. And from here, you can check your work, right? So the derivative of this should be that. So just check it. Derivative of 4x, 4. Derivative of 3x squared, 6x. Derivative of 12x cubed, 36x squared. Derivative of c, 0. Now we're only up to f prime. Look at the original problem. It says solve this problem, solve the boundary problem. We're given 2 derivatives and 2 points, but when it says solve, it means find the original function. So we have to find f. So we do another antiderivative. Leave the 4 alone. This becomes x squared over 2. Leave the 3 alone. This becomes x cubed over 3. Leave the 12 alone. This becomes x to the 4th over 4. The c now becomes cx. If you want to think of this as x to the 0, that's fine. You don't have to go into all that, though. And we have to tack on another constant, right? We've already used c, so you can't use it again. So we're just going to call it d. Doesn't matter what you call it. I'm just calling it d. Simplify. This time I rearranged it to put in reverse power order. So now it's in descending power order. You don't have to do that. It's just how I felt like doing it. Now, we're given 2 points. So here's the curve. So this part of the curve is known. This is unknown, and this is unknown. So it could be up or down, but also it could have parts of a line in it, right? The cx. So what we have to do is plug in our known values. So we were given that f of 0 is 2 and f of 1 is 13. So we just plug everything in. Right, so here we have f of 0, so 3 times 0 to the 4th, blah, blah. Everything with the 0 goes away. This is just d equals 2. Well, we know d equals 2. That's easy. And then here, f of 1. Plug everything in. It simplifies to 6 plus c plus d equals 13, because we know it equals 13. Well, if d is 2, 6 plus c plus 2 is 13, so d is 5. I'm sorry, c is 5. D is 2. Yeah, c is 5, right? 6 plus 5 plus 2 is 13. And then you go back to your f of x, and you fill in c and d that are known. So it turns out we had to do 2 derivatives, but in order to get a unique solution, we had to have 2 points on the curve, which we did. All right, let's keep going. So this is a physics application of antiderivatives. You have one just like this on the homework. I mean, a lot of the problems I do in the slides are homework problems. But this one is really sort of a good overall application problem. A stone is dropped from the upper observation deck of a tower, 650 meters above the ground. Find the distance in meters of the stone above the ground level at time t. So here's what we're going to do. Distance, then how long does it take the stone to reach the ground? We're assuming no wind resistance for all you people that like to bring up stuff like that. We know enough now that we could figure out what it is with wind resistance, but we're not getting into that. C, with what velocity does it strike the ground? And then D is a little bit of a different problem, right? If the stone is thrown downward with a speed of 3 meters per second, how long does it take to reach the ground? So let's think about this. So 650 meters is about 2,000 feet, okay? So, you know, not as deep as the Grand Canyon, you know? So just imagine how long you think it would take for a stone to reach the ground. And then if you throw it downward with a little bit of speed, 3 meters per second is like a kind of a wimpy throw. How long would it take to reach the ground, right? So just think about that. Do you think it would really, really increase its ability to reach the ground? So turns out we can solve all this with antiderivatives. So in chapter 2, we established this relationship between acceleration, velocity, and position, right? Acceleration is the derivative of velocity and the second derivative of position. So what we're going to do is we're going to say, well, we know the acceleration. Can we work backwards to find the velocity and work that backwards to find the position? Actually, we have to do that. That's what the problem is requiring us to do. So acceleration is negative 9.8 meters per second squared. That's a given. Okay, when you guys are doing the homework, if it doesn't tell you that, if you're in metric system, that is a known value. Or you can just Google it. Then you take an antiderivative. So acceleration is the derivative of velocity. So we take one antiderivative. You don't have to put the units on here. I just put it on the first thing, but you don't have to put the units on anymore. So the velocity is just the thing that would give us this as a derivative. Well, it's negative 9.8t plus c, right? If I take the derivative of this is just a linear function, so it's just the slope, right? Now, I have to establish what c is, okay? So c is a constant, right? But what does that mean? Well, here we're talking about velocity. So what is a constant velocity? Well, that's the initial velocity, right? Because whatever velocity an object starts with, it just gets added to its final velocity, right? It doesn't like lose some of its initial velocity, right? Just all the velocities add up when you're talking about velocities. All right, so now we know we need to look at velocity being the derivative of position. So I have to take the antiderivative of this, right? Well, we can see what's going to happen, right? This is going to be t squared over 2. Negative 9.8 divided by 2 is negative 4.9. Antiderivative of c is just ct, and then I have to tack on that d again when I do my second antiderivative. And d is the initial position, right? So whatever height the rock starts at, as it changes its position, that initial amount of height it had is still there, right? Like if you throw it down, you're still standing there. So this constant, this kind of translates to like this is a constant position. And you can see how this constant velocity is times t, right? Velocity times time is position. So this is just the setup. We're not ready. Now we're getting ready to solve the problem. So now we have all the equations we need. Let's plug everything in. So the initial velocity is 0. So for part A, the rock was dropped. The initial position was very high on the tower. So we just plug everything in, right? So initial velocity is 0, so c is 0, d is 650. And you can solve this when you're trying to find part B, you can solve this really easily. So that's the answer. So that describes the position if the object has just dropped, because only the acceleration is changing the position. Now we want to find out when the object hits the ground. We want to find out how long it takes, right, for the object to hit the ground. So you solve part A, set it equal to 0, and you just solve it. Right, it's very easy to solve with algebra. Again, I'm not showing the algebra. Make sure you can do the algebra. And you're going to get plus or minus when you solve it, but we're going to ignore negative times because we're assuming that t starts at 0. So you get 11.52 seconds. So if you're at 2,000 foot observation tower and you drop a stone, it goes 2,000 feet and 11.5 seconds. That's pretty fast. So this thing is going to be moving pretty fast when it hits the ground. So we take the time it took to hit the bottom and plug it into the velocity equation, right? And you get 112.87 meters per second. Oh, that should be a negative. Sorry, that should be a negative. I'll fix it when I post it. All right, well, that's part C. So negative means in the downward direction, right? The initial position was positive because it was an observation tower. It was above the ground. Here it's moving towards the ground. One of those has to be negative. One of them has to be positive. Now for part D, we have to take into account that there's an initial velocity of negative 3 meters per second thrown downward, but the initial position is still the same. And when the object hits the ground, s of t equals 0. So this time our s of t equation, we plug in c and d, and you get that. So instead of having a 0 for c, we have a negative 3. So it's harder to solve, right? This time you need the quadratic formula, or you could complete the square. Either way, you get 11.22 seconds. So starting that object with a little bit of a faster speed doesn't really cut down on its time, right? It's only about a third of a second faster, right? Because its other velocity right here was 11.52, so it was only 0.3 seconds faster, right? So it got to the ground a little bit faster, but not much faster. that's how you do it. So again, there's your quadratic formula, or you can complete the square. I mean, I don't care how you solve quadratics in this class. If you want to graph the quadratic and just find where it hits the axis, fine by me. You're not hurting my feelings. You don't have to show work for this kind of calculation. As far as I'm concerned, the quadratic formula is arithmetic, so you don't have to show work for arithmetic. But you need to show algebra work. All right, so that's it. So if you guys need more practice, here's some nice problems for you guys to work on. Let me know if you guys have any questions. And the next video will be starting the material that's on exam 4. So study hard, guys. And if you have any questions, let me know. So until next video, all right, goodbye then.